Welcome to the week 6 discussion of the course Fundamentals of Micro and Nanofabrication. So I am Udiptya, PMRF scholar from IIT Madras. So this time we are discussing uh, the section of metallization and optical lithography. So like the first two videos was on metallization, mostly on the first one was on contact resistance, that is how this metal, how we are depositing, like we are depositing various layers of metals, and how it is, like what temperature we should expose it to, and like you know that metal contamination is an important issue. So we studied all the effects of metal and how the it is changing the effect, like the material fabrication processes. Second was on electromigration. So depending on metallization, we also see effects of electromigration, that is these materials migrating in their own self under the influence of electric field, and some epilogues. So it was kind of a uh, uh, summary of the additive processing section. So we saw how some cumulative effects are there, and some generic cases around how this metallization works and what are the processes to deposit some of them as well, some of the common metals, the standard methods of deposition. So and then the topic of optical lithography starts with the pattern transfer, the different methods, direct, indirect methods of transferring the pattern to the substrate, that's where we want the pattern. And then the resist process, how different resists are there, photoresists are there, and the last one was continuation basically of on the resist put on photoresist. So let's go to the problems directly. So here this is a problem from the metallization section. So you have to identify the X here. So it's who am I, and you have to identify the contact or the metallization layer. So some of the properties, these are the properties of this layer X, which was what the layer X shows, and out from these four properties you have to tell which one of them is the layer X. Uh, so like this property, layer X forms spikes in silicons penetrating thin divisor near surfaces, has been represented here in this diagram. For this diagram has been shown. So you can tell which one of them you think is the correct one, and we will discuss. So these are the options. So these are the properties on the layer X, and these are the options, so you have to choose from them. Anybody? No guesses? I hope you understood the question, yeah? Okay, let's discuss the answer. So here you see the first property, that is the layer X is not very soluble in or diffusive in silicon, but silicon is soluble and has very high diffusivity in layer X. So like we saw that metals can, like anything can, any impurity or any material can diffuse into silicon. Similar things can also be done. You can think into vice versa, that okay, some material, like you coat, like you have silicon and then you have silicon and then you have coat it with a metal. So you can also see that this silicon can also can diffuse to the metal layer. So similar things are such kind of properties are shown here. So in layer X, like we can in aluminum, this case is one of the important thing. Aluminum doesn't diffuse much into silicon at the rate silicon dissolves into aluminum. Okay, aluminum diffusivity in silicon is very low, but the vice versa is very high. This layer X has resistivity. We know that aluminum is a very good conductor, so its resistivity is lower than 5 ohm, 5 micro ohm centimeter, and it reacts with silicon in the range of 250 to 300 degrees Celsius, and above that in these temperatures it forms silicides also, and above 300 degrees Celsius you can't go when we are using aluminum. So because like other materials, tungsten, you can go to higher temperatures, and they are very heat resistant, thermally very stable. So with tungsten, reactions are tungsten and titanium nitrides, tungsten silicides, they are very high. These are some materials that react at higher temperatures, not in the range of 250 to 300 degrees Celsius. And like this forms these spikes in silicon penetrating thin devices near surface. So what happens is that silicon from these places, these regions, they migrate to the aluminum. So what happens is they create some voids, and these voids are then filled upon by the aluminum. So this kind of looks like these spikes. So I hope it is so the answer would be aluminum here. I hope it is clear to you all. Okay. Any doubts you can ask? Otherwise, we can go to the next question. Clear? Okay. This is the problem 2. So you have to select which of the following is the desired quality of a metallization layer on device, chip or die. So it is a multiple correct question. Multiple of them can be correct. So just consider all the options, and whatever you feel you can type in the chat box. So like this is on, like you have deposited a metal on a like silicon chip. So what properties would be desired in such devices? So these are some of the properties that a device can show after you have deposited metal upon it. So which of them is the desired quality? you have to select them. Anybody? So the main thing is why we are doing metallization. So that is something you should keep in mind while we are discussing this thing. So then it would be more easy one to solve. So let's discuss it then. So here for a metallization layer, we mostly do metallization for get for having conductive property of our devices. So metallization. So you can construct devices that are semiconductor in nature, insulator in nature, and like depending on the coatings we do. Like for insulating, we do silicon oxide coating. So similarly, for metallization, layers are done to make a electrical contact on such devices. So the purpose of doing metallization is conductive part. So so the first option, that is lower resistivity. So as the prime, if the most of the like prime purpose here is to get a conductive path. So resistivity, lowering of resistivity is one of the important aspects of such devices. So if it's low resistivity, these channels will have like lesser resistance towards this current movement. So low resistivity is an important factor. It will have a lot of things like heat won't be generated much. So lowering of resistivity is one of the desired qualities. The thing is, the next thing is thermal stability to sustain high temperature processes. Step post metallization. So we know that like these devices we have to go. So there's like it's very rare that such devices have only one process of metallization. So complex devices nowadays, like these transistors and all, have multiple layering processes, multiple metallization processes. So in that, it has to sustain high temperature processes. So its thermal stability to sustain high temperature is one of the important things. And the last option is low electromigration. So you know that when if we have a channel like this, and we have current, movement of current in it, so electrons so essentially electrons will electrons will move in this direction. So this is what happens that like this metal constituents will due to the action of due to the movement of electrons, some of the material can migrate from one position and deposit here. So this place will be void, and this place will have this thing. So such kind of behavior happens. So these can also change the characteristics of the our device. So such a so so such kind of things are also to be avoided. So low electromigration is also an important aspect. As that our the native state of our device is maintained. So and we have discussed also how how we can lower electromigration, like having more defects, more not using the purer metal. We have seen that how it can affect the migration, and also the grain length, how that can also change. So some of the features, some of the things are there which can help in having a lower electromigration. So okay, I hope it is clear. Okay, let's go to the next one. If any doubts, you can ask. So this is also from the electromigration part. You want to tell anything? You want to ask anything? Okay. So this is the problem 3 regarding electromigration. So you have to tell which one of them is true. Okay, these are some statements about electromigration. So you have to select which one of them is true. Anybody? Which of the following statements you think would be correct? So last question also we were discussing about electromigration. So this is severe. Sorry. Nobody? Any guesses? let's discuss the answers then. So we have to see under which condition we see the electromigration, like the effects of electromigration here. So the first option is large currents cause less electron migration in the metal line than smaller currents. So this is one of the fundamental options. So that diagram we saw that if we have a conductor here and current is moving like this, so electrons will go like this opposite to the direction of current. So we see that when it will be more current means more electrons moving. So it should it will the constituent atoms here, uh, this constituent not atoms but these grains, these crystal grains will suffer more impact due to the electrons, movement of electrons. So more movement of electrons will cause more impacts. So the and this increases the chance of these grains to move out of their place and go to some other and shift to some other places. So large current essentially cause more electromigration in the metal line than smaller currents. Okay. So this is not correct. So the second option, addition of some impurities can slow down the electromigration by slowing down self-diffusion. So yeah, this is one thing that we have studied. So in some places they will add this some with some metals they will add some other impurities like copper or something, and such impurities essentially decrease the chances of the constituent metal to be migrate to the other places by stopping their self diffusion. So this is the correct one. And electromigration effects are more severe for the lines with larger grains. So this is something like you can see when these are if we have two situation, like we have very large grains, and here we have smaller grains. So what will happen if like you can if force is coming, if something is forced here, larger grains, the force component, it is very hard because to the electrons it will it will appear as if these are parallel walls. Okay, and pushing these parallel walls is very difficult. But you have this in smaller part, they are not arranged in a proper manner. So if you add force, such crystals can move uh, out of the way and they can migrate. So this is also not correct. And electromigration effects are more severe for high melting point metals. It's not such that. Okay, it is something that depends on the how the electrons are moving in it. So it is also not. Essentially, that has high melting points are more it is more anything that is high melting point are more stable in the such in a system. And you can see that aluminum, which has very low melting point, it will migrate more than the other materials like copper and all. So that's why it is correct. Okay. Let's go to the next one. So you have to tell which one among these processes has the highest energy of incident atom or ion. So we essentially saw that we can modify our silicon substrate, like silicon using different methods. These all the unit processes. So out of like among these processes, you have to tell which one of the process will have the highest energy. Okay. So a lot of processes involve impact using a lot of energy. So you have to tell which one of them is the highest energy. So like this is CVD, atomic layer deposition, evaporation, sputtering, and implantation. Nobody? Any options you think is correct? You can tell. We will discuss this further. If any doubts you have, you can discuss. Okay, should we discuss the answer then? Anybody? You can put your whatever your options you feel is correct. You can put it in the chat box and. Okay, then let's discuss the answer. So let's go from the highest, or should we go from the? Let's go from the highest. Okay, so the highest energy is something that we observe in the case of ion implantation. So in ion implantation, yeah. Okay. I think it must have been raised by. Okay. Okay, no issue. So the first, the highest one would be there in the case of ion implantation. So in ion implantation, what we do is we bombard the silicon silicon substrate with ions, such that we can have a doped region. So basically, the ions will go inside the silicon layer. So inside it, so it has a lot of, so it requires a lot of energy, and um, this is the highest energy of that out of this is the highest energy that we provide to a silicon, because other things are coating, mostly the coating, they are coating processes, but ion implantation is such, it is not as it goes to the bulk of the silicon wafer, so that's why it has the highest energy. Okay. So essentially this is the answer, so we'll discuss the other thing also. Sputtering, so this is the first. Then comes sputtering. So in sputtering, we have essentially electrical or electrical energy to generate plasma, and such that this plasma energy is then used for sputtering, like to activate the target and ions, and such that they can go and sit on the substrate, silicon substrate. So essentially we involve these atoms to energized atoms to come to the substrate. So that's why this comes to the second tier, second kind of highest energy. And then comes this CVD and ALD. Okay, so these are gentler processes. Okay, and then the evaporation. These are kind of like similar only, CVD and ALD. I think, yeah, evaporation I think it would be the more gentle one. And these are kind of similar processes which involve the energy ranges are mostly similar. But essentially the order would be the ion implantation, sputtering, and then evaporation and CVD ALD would be very close. I can't, I'm not able to recall like where how they are different. So that's the case. Okay. So let's go to the next one. So in this, a process engineer has patented a device using a lithography. So a process engineer is who like somebody engineer who designs such devices. So after exposure and development process, the patterns were found to be drifted away, though the features were sharp. So what could be the possible reason? So you have to troubleshoot. So the issue is that whatever pattern you have made has drifted away from their place. So drifted means it was in like X position, now it is in Y position. So drifting is something it has moved in some, like physically it has moved in some place, drifted away. But the features of that pattern is sharp. So whatever features you have you wanted from the lithography process, it has been paid properly with like all the features sharp and as desired. But the thing is it is physically displaced. So you have to tell which one of them is the possible, which could be the possible reason. So, what do you think would be the correct reason for the drifting away, although the feature has been sharp? So, uh, some process has been listed here, which are basically used using the process while we do lithography. So we have to tell which one of them must have not been like correctly done, but that such problem has been shown. Okay. Let's discuss the answer then. Uh, so the first option is that the photoresist was not baked before exposure. So essentially, let's go from the question side. Okay. So we can see this like we can first see how this thing has happened. So when we are designing our like how do you design how do you achieve such features? So what we do is we essentially have this portion that is the top view. We will the uh, coat the silicon wafer using a photoresist. Okay. So after and then we will expose it depending on the patterns. So basically, if we have this pattern, like we want a channel length, we want like this channel. So what we do is we if we use a uh, negative photoresist think so we will have a mask like this, like these are opaque regions, and this is transparent, and we have this silicon with photoresist coating, yeah, PR silicon. So what will happen is this portion will be there, and this is silicon. So this is what is the PR. But in this case, you are getting this this pattern is displacing. Okay. Uh, so the thing is, you have to understand how this. So the photoresist, you can see the photoresist has not been bind to the silicon substrate. Very like it is not been binded to the the silicon this below silicon properly. That's why it has been like it is being moved here and there, moved from the original position. So like it can drift any side. While washing it mostly drifts away. So the thing is we have to understand that this photoresist have a these are hydrophobic in nature, but our silicon is our silicon is something that is after we have treated after cleaning, it will have OH groups on the substrate. So for making these OH groups have hydrophilic groups such that the hydrophobic interactions can be made, because the hydrophobic usually this what happens is that hydrophobic groups tend to like hide their hydrophobic side by also binding to the hydrophobic surfaces. So mostly this when in a solvent form, when there is solvent around, it will mostly these things will come like this hydrophobic side will come together and they will bind. So that's why to modify the silicon surfaces to have hydrophilic surfaces, hydrophobic surfaces, we usually use a adhesion promoter. So adhesion promoter like HMDS is used such that you get coatings of silicon CH3. So essentially this alkane groups are hydrophobic in nature. Okay, so they will what and as the photoresist is also hydrophobic, they can also come and sit in the this and also like interact with the hydrophobic interactions. Uh, but this is something that protects like water. That is something, as they are not water loving. Hydrophobic is something that is not water loving. They will try to hide themselves by coming to close to the hydrophobic surfaces. That is what is the interaction property, and that's how this sticks to the silicon substrate. And if this adhesion promoters are not used, they will move around because this interaction is not so much strong that they can hold it. So the correct option is the adhesion promoter was not used. Okay, let's I hope it is understood by everyone. So I can proceed to the next one. Yeah. Okay. So this is a question from Photoresist. So our negative photoresist is sensitive to X-ray region. Is exposed through a mask using an eye-line source. So eye-line source here mean lambda equal to 365 nanometer source. So we have to select the correct answer. Which one of them is true for the same? So you have to see that which of the following properties is correct for such photoresist. D. Okay. Okay. You feel it's B. Okay. Anybody? Yes. Okay. Somebody C then. Okay. Nobody thinks C is correct. Okay. Maybe. Can somebody write what is the difference, difference between positive and negative photoresist? Just a small, what happens when the what happens in the positive and what we get in negative when light is exposed to them. Nobody? Just the difference between the negative and positive photoresists. Like,
Yes, sir.
yeah,
In positive photoresist, the exposed part is it is soluble, it becomes soluble, and it become then it will be aged with the help of some material,
Okay.
acetone or something. In negative, the exposed part is become solider, solid.
Insoluble.
Yes, yes. And the rest of the part then can be aged and pattern can be formed.
Yeah, sure. So essentially, yeah, whatever what is perfect is perfect. So to explain the other people, like whoever is there in the call, is that if we have, so this is silicon and we have a coating of PR. Okay. So this is the light. Essentially, this part is what, considering this part gets the light. So in case of positive one, okay, we will get a pattern like this. So as you told, this part will get soluble, and in negative we will get this part as, yeah. So this is what she wanted to tell. So this is the difference between positive and negative photoresist. You have to see now the question. Now I have to like read the question. So you got the things correct, yeah. But the thing is, you have to see that the question says that the a negative photoresist. So negative photoresist is sensitive to X-ray region and is exposed through a mask using an eye-line source. So X-ray region and lambda equal to 365 nanometer source. So we know that these photoresists are made in such a way that they are sensitive to a like a wavelength of a singular like they are very selective towards their what wavelength they are sensitive to. So here it is written that the photoresist is sensitive to the X-ray region. So X-ray is this part, and you are incidenting this thing with the ultraviolet uh, source. So that thing that X-ray are like it's very the wavelength is very small compared to what is in like 360 like this lambda of 365 this eye-line source. So the first option, that this photoresist is incompatible with the source, is the correct one. The other option doesn't come in place because the thing is it is we have to use the photoresist depending on the source, or actually we have to like the vice versa, the source and the photoresist should match, and that's how we get a pattern. If it doesn't match, if they are not the compatible ones, we won't get any patterns. So the B and C options are invalid in nature. Yeah. So you have to read the maybe read the option questions first. Okay, what the photoresist is sensitive to, and what are the light sources that are present, and depending on it, you will get things. Right. Okay, fine. But this thing was like the positive and negative. That thing was totally correct. Okay. So yeah, perfect. So this is a question of this we are using spin coating for laying the like for spreading the photoresist on a wafer. So this you have to tell these are two conditions, A and B. So A and B are two conditions. So in A we are using identical photoresist, but the spin speeds are varying. Okay, and in B you are using two kinds of photoresist, X and Y. So but they have difference in viscosity. So you have to tell like which one of them is correct. So so we have two options: omega 1 greater than omega 2, or omega 1 less than omega 2, depending on like thickness and time graph. And here like both the graphs are thickness and time. So you have to guess which one of them, like taking the first one, we have to guess which one is the faster spin speed, the lower spin speed, depending on the seeing the graph. So here we have identical photoresist. So essentially they will have similar the material properties will be similar, same actually. But the only thing is we are using different spin speeds. So first one, let's solve the first one first. So just you can type whatever you feel would be a correct one. Okay, let's discuss. Uh, Essentially, you can see that when we like this is the rotating chuck, which we are basically this is the rotating chuck is where we place our wafer and it is rotating. So you can see that when it is rotating at lower speeds, and you have dropped photoresist here and it is rotating at a slower speed, this it will experience less centrifugal force. Yeah, then what will happen is it will because centrifugal force is essentially it is omega square r. Yeah, so it is directly proportional to the omega that is present, like the centrifugal force. Yeah, so when we are providing lower speeds, the rate this photoresist will experience the force will be with low spin speed, low force. Yeah, so it will spread slowly. Okay, so essentially when we have higher speeds, it will spread uh, faster, it should spread faster, and then if it is spreading faster, the thickness will also decrease. Yeah, because if it has spread a little only, like because the mass is same, only like it has spread like this and it has spread completely. If in two conditions, the material having completely spreaded, it will have a lesser thickness. So essentially, which one will have the chuck having a higher speed, it can spread it like fully, and it will have a thickness that is lower than this one. So essentially, the lower one, the omega 2, will experience more force. So this will be higher. So omega 2 will experience more force. That's why less thickness, and omega 1, then omega 1. So this is the correct one. Okay. So more force means less thickness because the amount is constant. Yeah. And the second one is having identical spin speed. So omega is constant here. So your this essentially this force is constant, the centrifugal force, but you have to see the viscosity. So if you see, viscosity is something that is the friction between the the layers of the liquids. So essentially anything which is more viscous will have more friction. So it is an opposing force, like it is going to it is trying to spread, but something is like pulling them against it. So anything that will have more viscosity will spread slowly. Essentially x is spreading slowly, that's why the thickness is more. Yeah, anything that spreads slowly will have more thickness. So essentially x is spreading slower than y. So we can see that X is more viscous than Y, like that. Okay, I hope I am clear to you all. Okay. So this is a question from the lithography process, like how the three modes of exposures, and depending on the distance we have three modes: contact, proximity, and projection. So which of them is a false regarding the like the statements? Which one of them is the false option? So you have to tell that. So essentially, this is like if you have a silicon wafer and this is the photoresist, depending on where we place the mask, like if the mask is in totally like the distance is very less, we called it contact. The distance is appreciable, we called it proximity. And if it is very large, there we use this lenses system. These are lenses. This is mask. These are masks. Okay, and we use this is the substrate here, silicon. So we use lenses, the light, then we call it the projection. Okay, so which one of them is the correct one? Okay, anybody? Nobody? Should we discuss the answers? Because time is running out. Okay, anybody? You have made any, you think? Okay, maybe we can discuss the answer, yeah? Because time is a constraint. So the first option, the effect of diffraction of light is minimum for contact lithography. So we have to remember that we have to find the false one. So when the mask is in contact with the PR, very less space is there for the light to be diffracted. So for essentially the light diffracts when we have a pattern, we have a gap here, and light will basically diffract in these different directions. It don't come parallelly. So essentially when we have the mask is in contact with the directly the photoresist, there is very less physical space for the light to be diffracted. So in such conditions we can get very minimum contact lithography. So very minimum diffraction of it, which is true. So in contact, so the second option is in contact mode, the most mask can be contaminated by photoresist during alignment. Yeah, this is true because as the contact is in contact mode, the mask is in complete like touching the photoresist, so it can get contaminated. True. And the contact mode cannot support batch production. This because when we are this is true because in contact mode we essentially are using like we are using like it can a minimum it can go is that it can only like feature size is something that is it can make feature size that is equal to the mask size of the masks. Okay, size that feature whatever the dimensions whatever is in the mask, that is the least it can go. Okay, but in some other like in projection you can you can uh, you can make features that are less than the size of the masks, so that's why you can't support batch production. So this is also true. And in contact mode of exposure, it can give a better resolution than the other two modes. Essentially it is not true, because in projection one you can also, like, you can have, because of the lens system, you can go to very lower resolutions. So therefore essentially the projection mode will have the highest resolution, and this is the false one. So this is the false. Okay, so okay, let's stop here then, as time has ended. I had made two questions, but hopefully I don't know if it's should we continue, or should we stop the class?
Continue,
Okay,
please.
okay, two questions are there, we can. Okay. So this is a quick question, and last I have a numerical, so that you can take. Okay, so this is a question on HMDS. What is the correct function of HMDS? So these are the four statements. So okay, so nobody, any answers? Okay, so as we discussed in one of the questions, that HMDS is a adhesion promoter. It helps photoresist to establish this hydrophobic interactions. So the first option, that is the photoresist coating to increase adhesion of the photoresist, is the correct one. This is essentially correct. The other option is HMDS layer is generally very thick compared to photoresist. It is not true, because it kind of forms a monolayer over the it is very thin layer, like mono, or some atomic layers only, that is there present in the over the silicon substrate. And it is an etchant that increases roughness of the substrate, increasing adhesion of the photoresist. So it is not an etchant. Etchant is something that etches the material out. So it is not a case. And it is used to change the optical property of photoresist, so the photoresist can be exposed using light of another layer. No, so it doesn't essentially change the optical property of photoresist. So the option 1 is the correct one. Okay, and okay, the last one. So suppose if the photoresist medium is inhomogeneous, and alpha is the function of depth, such that alpha equal to alpha naught z, where alpha naught is a constant. At what value of z in micrometer the intensity of light after absorption remains 37 degrees percent of the 37% of the initial value. So you have to take alpha naught using equal to 2 micrometers, 2 micrometer negative square. So use I think we'll incur you some calculator, so you can use, you are free to use. So just to give some hints, this refers to the Beer-Lambert's law, this I equal to I naught e to the power alpha z, that we studied. So you have to go in these lines, and then you can solve it. So we will wait for some time, and we will solve it together. So essentially you solve whatever answer you get, you just put it in the chat box. I will also have to solve it, then only I will get the answer actually. So whoever has missed the earlier sessions can view them in the YouTube video section. So that is present in the problem, like in the course page only. you will see in the down it will have problem solving sessions, so you will get the YouTube videos, also the PPTs that we are solving. And I think in last class also we were not able to solve all the questions, so like all the problems we were not able to discuss because of the time constraints. So some 2-3 questions are also there in extra that we didn't discuss in the session, so that might also help. And if you have any particular doubts, you can mail or directly comment on the YouTube comment section. We can take that up. So anybody solving it? Let's solve it then. Okay. Here it is given that at the intensity of light after absorption is 37% of the initial value. So considering initial value is I naught, we will take an initial value of light intensity. So final is I is 37% of I naught, essentially 0.37 I naught. So if we put it here in this equation, 0.37 I naught equal to I naught into e to the power alpha z. So I naught will cancel, and 0.37 equal to e to the power. So alpha is equal to alpha naught z. So and this z is always there. So this is the thing. So we can take ln in both the sides, then we will get equal to this will come down alpha naught z square. Okay, and essentially alpha naught value is given alpha naught value is 2. Okay. And this root is what will get the z. So has anybody solved it? Okay, and I will use the calculator. ln okay, this value is coming 0.49. Okay, z, and so z is essentially therefore z is equal to 0.7 around. Okay. Okay, so this kinds of ends this session. If any doubts, you can stay back. Others are free to leave. So thank you for joining, and we will meet in the next week, same time, with week 7 discussions. Thank you all. Sorry for going overboard like with some minutes. So